So here is the data set, adjust r square, and then we'll try to build a model 1 m1 with 3 variables. So m1, if we see the summary, we can see an r square of 68%, adjusted r square of 56%. So there are 3 variables. Out of that, one of them is non-impactful, remaining 2 are slightly impactful. That is fine. Now I'm going to add 3 more variables, trying to build model m2. So what we are going to observe, r square might increase from 68 to something else. Let us look at what adjusted r square is going to do. If these variables are not impactful, if they are junk variables in this context, then adjusted r square should not increase. R square might or may not increase. So when I build model m2 and look at its summary, r square increased from 68 to 71. Adjusted r square actually dropped from 56 to 37. Why? Because in this particular data there are too many variables that are non-impactful. In fact, in presence of other variables, even previously impactful variables are gone down as non-impactful variables. We will go further and even increase the number of variables by 3 more, 2 more. Let's say even for this model, right now r square is 71%. I want some more r square. I'll add 2 more variables, x7, x8. And then see the summary. R square even further increased to 80%, adjusted r square even further reduced. That is what happens whenever you build a model. If you are trying to add more and more variables, even if they are not related to your target variable, then there is a problem. R square is not capturing that. R square simply keeps on increasing as and when you are adding the variables. We need a better measure, that is adjusted r square. So adjusted r square kind of keeps a check on the number of variables that you should add. Also, we have to observe that if r square and adjusted r square are nearby, if r square and adjusted r square values are almost equal, what does that mean? That means there are no junk variables in the data. If all the variables are impactful, if all the information that we are providing to the model is actually impacting something or the other on the target variable, then r square, adjusted r square will be anywhere nearby. If r square, adjusted r square are far away from each other, then we know that there are some variables in the data that are not useful for this particular model. That's it. Now that we understood adjusted r square, there are some other issues in multiple regression. We'll try to focus on some of the other issues in multiple regression. So we need to do a lab to understand what are the other issues in building multiple regression line. Okay, you can do the lab along with me. What are we trying to do here? There is final exam score data in our data set. You have to import the final exam score data. You need to build a model to predict the final score using rest of the variables. There is one final score variable. We need to build a model using final score, to predict final score using rest of the variables. And then we have to do all these one by one. So let us do all these questions one by one. So first we need to import final exam data. Where is this data set? Let us try to get this data. Final exam score data. I want to name this as final underscore exam. Be careful, make sure the heading is yes, otherwise if you're saying heading is no, then it will be v1, v2, v3, v4. Rather we should keep heading yes. There is heading in this dataset. This is the final exam data, which has one final exam marks: semester 2 mathematics, semester 1 mathematics, semester 2 science, semester 1 science. These are the 4 variables. Using these 4 variables, we want to predict final exam or some other external exam, CAT or something. Depending on these 4 internal marks, we want to predict the final external marks. We are trying to understand a particular phenomenon in multiple regression. For that we are doing this simple example. So these are the dimensions 24 and 5. And these are the number of variables that you have in this model. Now what are we trying to do? We are trying to predict final exam marks using semester 1, semester 2, semester 1 maths, semester 2 maths, right? And then this is the summary of that model. From the summary, it is clear that R square is 98%. Adjusted R square is also 98%. That is a good scenario. Now that's really good. There seem to be everything that is there in the model seem to be somewhat or the other affecting final exam. Let's say semester 2 mathematics, semester 1 mathematics, and all that. Okay, though it is not significant, but it is not totally unrelated. It's not really junk, or it is related somewhat to final score. That's why R square, adjusted R square are nearby. Now there is a slight issue here. If you look at semester 2 mathematics, it is negatively impacting final score. You see the coefficient of semester 2 mathematics. Semester 2 mathematics is negatively impacting final score. Why am I saying that? Because the coefficient is negative. That means if someone scores very less marks in semester 2 mathematics, we are going to tell him that he is going to score real good marks in final exam. Now that is counterintuitive. How can you actually score less, or let's say if someone scores really low, only 10 or 15 marks, he doesn't study anything in semester 2 mathematics, then he might score real good marks in the final exam. That's what we are saying according to the model. That's what the model is saying. Now what I'm going to do is I'll keep the data as it is. Semester 2 mathematics, I'll leave it as it is. Final exam score, I'll leave it as it is. Everything I'll keep the same. Only one change I'll do. I'll drop semester 1 mathematics, which is totally not there in the discussion, but still I'll drop semester 1 mathematics. I'll drop this variable and see what happens to the model on the same data. I adopted a totally different variable, semester 1 mathematics. Now suddenly semester 2 mathematics is positively impacting. On the same data, earlier I was saying that if you study well in semester 2, your final exam will be low. If you don't study well, final exam will be high. So earlier these two variables were inversely related. Now on the same data, we are saying they are positively related, like if one increases, the other one increases. To have a good final score, you need to have good semester 2 mathematics marks. Just before this we said to have a good final score, you need to have less marks in semester 2. There is something wrong. There is something really unusual happening in this model. What is it? Basically, when we dropped semester 1 mathematics, semester 2 mathematics variable started behaving differently, entirely differently. Why is that? In fact, for model 1, R square, adjusted R square, 98, 97. For model 2, R square, adjusted R square. So this is model 2, I think. Okay, let me make it model 1 and model 2. So summary of model 1 and summary of model 2 will see. So this is summary of model 1, R square is 98%, adjusted R square is 98%. Summary of model 2, R square is 98%, adjusted R square is 97%. So they're perfectly good models, both of them. But only thing is that when you are trying to find, or when you are trying to analyze the impact of individual variables with the target variable, then there is some counterintuitive inferences that you need to draw. Why? What is that problem? That is due to a phenomenon called multicollinearity. That is due to interdependency between semester 1 mathematics and semester 2 mathematics. Sem 1 math, Sem 2 maths are highly correlated, or they are highly related. That is the reason why the coefficients are going for a toss. So when there is multicollinearity, or when there is interdependency between the predictor variables itself, then the model coefficients might be wrong. This phenomenon or this interdependency between predictor variables is known as multicollinearity. Is there really any interdependency between the predictor variables? Let us see. Let us draw a scatter plot between semester 1, semester 2 mathematics. As sem 1 math increases, sem 2 math is also increasing. Find the correlation between sem 1 math and sem 2 math. Right? It's 99%. So there is a 99% correlation between sem 1 mathematics and sem 2 mathematics. That is the reason why we can see there is an issue with the interpretation of semester 2 mathematics relation with final exam marks. So this interdependency between the predictor variables is known as multicollinearity. Multicollinearity is an issue because the coefficients that we are getting in presence of multicollinearity are not trustworthy, because multicollinearity, this interdependency, actually really inflates the variance of the coefficient, so that is a problem. So we need to detect multicollinearity. What is multicollinearity? Interdependency between the predictor variables itself. If the predictor variables, they themselves are dependent, then that is called multicollinearity. If that such interdependency exists, then we have an issue. That interdependency is known as multicollinearity. So one has to do multicollinearity detection, and we have to treat multicollinearity. We have to make sure that we reduce multicollinearity or we remove multicollinearity. Then only we have to trust the coefficients.